All right. Did we switch over, Jeff? All right. So I get to start this now. Thank you all for coming. It's a lot better day than I thought it was going to be. I thought it was going to be much hotter in my gear, but welcome to United Astronomy Clubs of New Jersey. We are streaming this live to our YouTube channel. So if you're ever not able to make it here, or helps if I turn the volume down because I'm starting to hear myself. I'm like, why do I hear myself? All right. If you can't make it or you have other plans, feel free to check us out on our YouTube channel. We have all our past broadcasts from when we were able to open after the pandemic first hit till now. We do keep those online for you guys. And if you have any interest in any of our past broadcasts, they're an excellent resource to use. So a couple housekeeping things before we go. We are a nonprofit, so we thank you for coming. All the donations that we have collected and whatnot have gone to keeping us up and running, our lights on, and us offering free public presentations for you guys, and done a couple upgrades, such as getting a new projector, so now that our live audience can actually see. Because unfortunately, the biggest star, or not the biggest star, the closest star to us, the sun, is not great with projectors. Who would have thunk it? So if you guys here in our live audience need to use the bathroom, we do have the porta potty to my right, your left. We also have a gift shop to my left, your right, should you want to check that out after the stream. Also down there we have several sheds. Each of those sheds has a roll-off roof and does house a telescope, which normally in non-pandemic times we would invite you in to view through the eyepiece. When it's clear, we have been, with the pandemic, doing electronically assisted astronomy, which is where we attach a camera to the where we would normally put the eyepiece and actually project that onto a screen onto the side of the building. So I'm kind of hoping, fingers crossed, that we do get some clear skies, that maybe we could see something tonight. And with that, our presentation tonight is going to be the latest lucky imaging results using the 13-inch Schupmann telescope at Stellafane and the 6-inch Warney and Swasey refractor at Mount Wilson, with Thomas Spirock. Spirock? Spirock, yes. Okay. In this presentation, he'll present the latest results using the lucky imaging technique, and that's in quotes, so I'm guessing that's a special procedure, with these telescopes at Stellafane and in Springfield, Vermont, USA, and at Brashear?
Brashear.
Okay. Words that are difficult for me to pronounce. At Mount Wilson in Southern California. And first, the unique and advantageous I need to unwrap my tongue from around my eye tooth so I can see where I'm talking. The characteristics of the Schupmann telescope will be discussed, along with a brief history and description of the 6-inch W&S refractor at Mount Wilson. And then the lucky imaging technique will be described. And finally, a comprehensive list of resulting images will be presented, including Mars, Jupiter, Saturn, and both full disk and high-resolution images of the moon. Thomas Spirock has been a member of the Springfield telescope makers at Stellafane since 1989. He was instrumental in building both the 13-inch Schupmann telescope and the McGregor Observatory at Stellafane, both of which were completed in 1995. He earned a PhD from the New Jersey Institute of Technology, working to develop the latest iteration of the solar vector magnetograph. The small words I can't get, but yet I can get that one. At the Big Bear Solar Observatory in Southern California in 2005. During the past several years, he has been applying the lucky imaging technique to data collected with both telescopes and a 16-inch f10 Meade catadioptric and the 60-inch Cassegrain telescopes at Mount Wilson. And with that, here's Tom.
Okay. The mic is working correctly?
Yep.
Okay. Thank you for inviting me tonight. I'm going to give this presentation sitting down. Speak loud. Okay. I'm going to give this presentation sitting down so I can use How's this? Any better? Okay. So I'm going to give this presentation sitting down so I could use the mouse as a pointer, which I believe you can see there. Okay, this is a brief outline of the presentation. First, we'll briefly talk about what is Stellafane. We'll talk about what is the Schupmann telescope and why do we want to use the Schupmann telescope. Some recent improvements to the Schupmann telescope. Very brief, we'll talk about the 6-inch Warney and Swasey refractor at Mount Wilson in Southern California. We'll briefly talk about the lucky imaging technique. However, this is not really a how-to because that would be far too long for a brief presentation like this. And then we'll talk about some latest results, including some high dynamic range and then some ancillary results. So very briefly, what is Stellafane? Strictly speaking, Stellafane is Latin and Anglo-Saxon for Shrine to the Stars. And it's the name of the pink clubhouse of the Springfield telescope makers in Springfield, Vermont. However, it's also been come to be known for the annual Telescope Makers Convention that's held every July or August. Stellafane. You see it? Oh, okay. And then this lower picture is a picture of the people setting up their telescopes at the Stellafane Convention. Stellafane and the Stellafane Convention was started by Russell W. Porter. If you'd like to learn about him, there's a biography you can find online, buy it used. And this is Russell Porter grinding and polishing a telescope mirror. And that was the purpose of Stellafane, was to teach people how to make and use their own telescopes. And this was the first telescope making class he started in August of 1920. So it's just over 100 years old. The first official meeting of the club was December 7th, 1923, and the first convention was 1926. And they've been going pretty much ever since, except for during World War II and unfortunately last year. But we are planning on having a relatively normal convention this year. And also history is very important to Stellafane. These are two pictures taken from approximately the same place, several decades apart, and they basically look pretty much the same. So if you're interested, you should check us out online, stellafane.org, and see about attending. So what is a Schupmann telescope? Schupmann is it's a different type of telescope than most people tend to think about. Most telescopes can be classified either as a reflector or a refractor. Reflector uses mirrors, refractor uses lenses. Well, Schupmann is a hybrid. It uses both mirrors and lenses to try to optimize the image we get. And there are very few of them have been made, and Jim Daly, he's one of our members at Stellafane, he's basically the world expert on making Schupmann telescopes, and he wrote a book about it. I'm sure he'd be happy if you bought one. He doesn't sell too many, I don't think. But if you really want to learn about the innards of the Schupmann, you should get this book. But we're just going to go over some brief characteristics today. So first thing is we'll talk about is why do we want a Schupmann telescope? And the whole point is to take a nice pretty picture. And in order to do that, you need to capture the most subtle details of your target, whatever your target happens to be. So you want to minimize anything that would disturb catching the most subtle details. So these are some of the characteristics which we want to find. Perfectly achromatic refractor. Achromatic is just a fancy word meaning no color, which we'll talk about shortly. No central obstruction. A refractor, which is the kind of telescope which you look like from the end, like on a pirate ship, has no central obstruction, meaning there's nothing in the way of the light coming through the telescope. We also can correct for atmospheric dispersion, which I'll show you some pictures of. Also, one problem with mirrors is that they scatter light, and scattering light tends to hide your subtle details. So we want to make sure we minimize our scattered light. Also, the mirrors are smaller. If you have, for example, a 8-inch Newtonian telescope which uses a mirror, if you had an equivalent 8-inch Schupmann, the mirrors that we use are smaller. Therefore, any scatter that does come from the mirrors is less. And also, the optics are easier to make than complicated refractors. And we'll get into all this in a little bit of detail shortly. So this is a picture of our the large Schupmann. It has a 13-inch primary single lens up here at the front. It focuses the light to the back, a 2.5-inch mirror called a field mirror, and that has a bit of a curve in it, and that refocuses the light up in the center peak here to an 8-inch mirror. And this is a bit of a special mirror. It's called a Mangan mirror, and it's actually a combination lens and mirror because we grind and polish both sides, and the reflective material is and then comes back out again. It goes through the glass twice, and then it hits a right angle mirror, and then we look at it or put our camera there. So this is we'll talk about the chromatic aberration, which again is color. Whenever you send light through a lens, each color acts a little differently. So if you have a single lens, white light is composed of all of the colors of the rainbow, but when it comes through the lens, it gets split. The blue light focuses closer to the lens than the green, and then farther still is the red. So this would make a very poor image. Over here on the right side, this is simply a plot of the x-axis is the wavelength, which is just another word for color. So red is the 700, green is about 550, and blue is 400. And this blue line here shows the focal length as described in these 3 lines, the position of where each color focuses. And we see that this y-axis is focal length, that each color has its own focal length. So this shows that this is a very poor configuration for a telescope. So one solution is you can put a second lens, and that helps us a little bit. We see that the colors are focused a little bit better, and that right now we're on this red line, and this shows that we're on this yellow line. This shows that we're better than the blue line, but still not very good. Another solution is we can put a third lens, and that gets us even better. Now we're on this red line, and we see that the focal length of each color, this is the blue, the green in the middle, and the red, are very good, but still not quite perfect. We also have to keep in mind that we now have 1, 2, 3, 4, 5, 6 surfaces to worry about. And so this starts to get a little complicated to make. So this is a schematic of a Schupmann. So what we have here is a single lens, as we show in the previous picture, and that focuses on this field mirror, and we see that all the colors are very separated, which is bad. However, this field mirror re-images this image onto this back surface mirror. Again, we see that the silver, which is the reflecting material, is put on the back. So the light goes through the glass, hits the silver, and comes back out through the glass. And if you design and build all this correctly, out comes the white light, which is the same as went in. So this is essentially like a refractor, but has 0 color. And so we can then put our eye here or our camera here, and we have a nice image with 0 color. Another reason we want a Schupmann, as I said before, is there's no central obstruction. This is a sample of a Newtonian telescope that someone built, a young person built and entered at the Stellafane competition. And the mirror that reflects the light is in the back. The light comes from the star from the top, goes down the tube, hits the mirror in the back, and then comes to a focus. But if you were to put your head in the way to see it, you would block your image. So what we have to do is put a right angle mirror here to move the light so it comes out the side so we can look at it without interfering with our view. And this is a picture down the tube, and we see this mirror. The problem is that whenever you put anything in the way of light, we get scattering and diffraction. This is a computer simulation of what there would be with no central obstruction, and this is a computer simulation of with the central obstruction, and we see that these outer rings are getting brighter, and that means that there's scatter going into other parts of our image, which will cloud out our fine detail. So a Schupmann and all refractors do not have this central obstruction, which is good. Another reason is we talked about fixing the color. Well, one thing that this field mirror and the rest of this second half of the telescope, it doesn't care where the color comes from, whether it comes from this glass in the primary objective or it comes from the atmosphere. As we showed in this picture, this is a cartoon of Saturn, and actually this is applicable right now because Saturn is very low on the horizon to the south. As the light of Saturn comes through the air actually acts like a little lens, and as we saw before, whenever light goes through a lens, it gets split into its colors. So this is an example of what might happen. You don't see it this poorly. This is just a cartoon demonstration. But each of those colors gets smeared out a little bit, so you can't quite get a good image. And part of the edge of Saturn will be blue, and another part will be red. So what we can do is by adjusting the tip and tilt of this field mirror, we can remove this color, and Saturn will look as if there was no air. No other type of telescope can do this. And again, right now for Saturn and Jupiter, this is particularly applicable because they are very low, and so they're going through a lot of air. Again, we talked about mirrors scatter light, and scattered light smears out the fine detail. So basically, when you put the Mangan mirror, which is about 8 inches, plus the field mirror, plus our fold mirror, we have about half of the surface area as if this were an equivalent Newtonian. The Newtonian was that yellow telescope made by the young person. So we have half the area, we have half the scatter, and less scatter is good. And that's a picture of the Mangan mirror with Jim Daly reflected in it. Also, we said that these optics are easier to make. It is true that there are more of them, so that's a little bit of a problem. But in general, they're smaller. Spherical simply means that they're easier to make. That's optician's lingo, meaning that the optics are easier to make. And also this wedge sensitivity, which is basically how thick the lenses and mirrors have to be. Again, that's some more optical lingo. Basically, this all means that the individual optics are easier to make, and they are more tolerant to mistakes. So again, this is a schematic. This is actually a painting on the side of our wall of the observatory. We see the telescope here. On our east wall, we have a painting. This is a close-up. One of our members did this several years ago. So again, we have the single 13-inch lens. It comes to a focus on a 2.5-inch field mirror, which diverges onto this 8-inch back surface Mangan mirror, and then it comes to a focus, and we can either put our eye or a camera. Now this is not necessarily an improvement, but one thing you have to do whenever you're trying to take image subtle details, you have to make sure your optics are very clean, because you can have the greatest telescope in the world, but if its lens is dirty, every piece of dirt acts to scatter light. And again, we're trying to minimize scattered light because that clouds out our fine details. So you always want to make sure your optics are nice and clean. In general, people think that cleaning optics is a bit of a black art, and it's really not as difficult as most people think. Modern glasses are pretty tough, and this is our 13-inch lens, and we're literally using a Windex and Bounty towels here. You basically spray the lens, you dab off the big pieces of dust, you spray it again, and you rub it down until you get rid of all the dust. And there's our nice clean lens. So we will minimize our scatter from any dust. Another improvement we recently made was reflective coatings on mirrors. They don't last forever. They degrade over time. And So this is the Mangan mirror, about 8 inches in diameter, and this, remember, this is the back surface. So there's silver was put on the back surface and then painted black to protect it. Well, over time, the atmosphere eats away at these coatings, and these coatings start to tarnish, kind of just like a silver spoon. You might leave it out, you have to polish it later. So this coating started to tarnish, so we had to send it to an optical coating company who does this professionally. And this, so now we have a nice new coating, and this is Jim Daly remounting the mirror in its housing. And so this is the housing of the mirror. It has these tip-tilt controllers, so we can adjust the alignment of the mirrors to make sure everything's properly aligned. And this is the holding plate, and this plate gets mounted up near the pointy part of that telescope. And once you mount all your optics again, you use a laser to make sure that everything's aligned, because again, you can have a nice clean optics, the best telescope in the world, but if the optics aren't aligned just right, you're not going to get a good image. So this is that field mirror we keep talking about, and it has a little cover to protect it from dust and a target on it. And with the lights out, you can see that the laser, which we shine into our eyepiece where we would put our eye or our camera, and it comes back to the center of this field mirror, and that tells us that everything is aligned properly. So I don't exactly know how, what people's experience about looking through a telescope is. So this is an example of Saturn, kind of a live image looking through a telescope. And what you see is that Saturn is not just sitting there still, it's kind of wavering. And that's because of the atmosphere that's passing between Saturn and our telescope. And that's caused by various heat waves, just like when you're in the desert and you look down on the road and you see a mirage. That's caused by heat, heating the road, distorting the air above the road. We have the same basic effect when we're looking at the stars. The analogy is looking at the stars and the planets from the bottom of the atmosphere where we live is equivalent to bird watching from the bottom of a swimming pool. It's basically the same idea. So one thing is we want to try to reduce this wavering. Now this is, we're not going to get into anything, but there's this physicist called David Fried, and he basically studied the physics of the atmosphere, and he came up with this equation that tells us what's the probability if we take X number of good pictures, how many good ones are we going to get? And what this shows us is this big D is the diameter of our telescope. And the point is, as your telescope gets bigger, the probability of taking a good picture goes down. And this is a line plot of that equation, and this is telling us that here, for example, this blue line is a 12-inch telescope, and the green is an 8-inch telescope. This x-axis is the quality of our seeing, which is how much Saturn is jumping around, and this y-axis is how many pictures we have to take to get one good one. Well, if you go from a 12, we see that, for example, at this point, we have to take 2,000 pictures with a 12-inch telescope, but if we have an 8-inch telescope, we only need to take 10. So there's sometimes a big advantage to using a smaller telescope. You actually get better pictures. So there's two ways to do this. Having a given telescope, you can put what's called an aperture stop. So for example, you have a 13-inch telescope, and for example, you want to make it 9 inches. You basically can put a plate in front of your telescope. Is my mouse gone? Oh, there it is. You can put a plate in front of your telescope with a 9-inch hole, and you've converted your telescope from 13 to 9. But we've done it a little differently, is where we put a moving plate in front of our Mangan mirror. So it's very easy for us to change from 13 to 9 inches. And this is, again, Jim Daly. He's installing this plate. We see this is a rod which it rotates around, and there's this piece of metal with this hole cut in it. So on the right side, this piece of metal is removed from the optical path, and we have our full size. And if you put this piece of metal in the optical path, we now have a smaller telescope. And this is Jim Daly, he's installing this rod. It's kind of, we're trying to keep to the old ways. Instead of having an electronic motor with push buttons and a battery, we're kind of doing it as they would have done 100 years ago with pulleys and push things such. And so you simply take this little handle and you can either push it in or pull it out, and you can very easily convert our 13-inch telescope here on the upper right to a 9-inch telescope here on the lower right. So that's basically it on the Schupmann telescope. This is a 6-inch Warner and Swasey refractor at Mount Wilson. It has a Brashear lens. Basically, these are very high-quality companies back about 100 or 120 years ago that were in the business of making telescopes. This telescope was installed approximately 1910 up at Mount Wilson. Mount Wilson is above Pasadena, California. And it's a very famous observatory, and it's known for its very good quality seeing. As we saw in that picture of Saturn, Saturn would not be wavering around very much. And this was in storage for a while. They, a few years ago, reset this up and refurbished it. So we've also been using this to take some images. And also, as we see here on the right side, this telescope has been kept as it was 100 years ago. It actually has a weight-driven drive. So there's this motor here. The motor doesn't actually turn the telescope to follow the stars. It raises up this weight that's in the pedestal, and as the weight falls, it turns these gears, which turns the telescope to follow the stars. That's how they did things 100 years ago. So now we'll talk about the lucky imaging. And yes, it's correct that lucky imaging is a specific technique. So I'm just going to read this one sentence because I think it's a little important. Lucky imaging is the process of capturing and saving many short exposures as rapidly as possible and selecting the good ones, good images, to be aligned, averaged, and enhanced in post-processing when we do that later. So just, again, we're back here now on Saturn as if you were looking at it through your telescope. So what we're doing is we're taking many as possible of these pictures, and if you notice, sometimes Saturn is better, sometimes it's worse. So we let the computer figure out the good ones, and then we throw all the bad ones away. And this is our steps. So first we capture those raw images, and that's what we're doing at night. And then everything else you can do later with the computer. Sometimes maybe Saturn is moving around, so you might want to pre-align it. You then have a computer program that selects the good images, and then it aligns them up and averages them, and you get a much better picture. Wavelet processing is just another fancy word for doing some image processing to make the picture, and then whatever other processing you'd like. But steps 2 to 5 are all done later, away from the telescope. And again, this is our live image of Saturn. It's wavering around. We're taking hundreds and thousands of pictures, and then later we're picking out the few good ones and using them. So that's why it's called lucky imaging. If you look long enough, you'll get lucky and see a few little good images. So one thing you do is you need a camera that takes pictures and saves them as fast as possible. Now, I use it from a company called ZWO. There are other companies, and if that's what you want to use, that's fine. Basically, I find that there are it's nice to have two types of cameras. One has a small chip for the planets, and you see this camera costs on the order of $149 for the color version and $179 for the monochrome version. I tend to like the monochrome. And the basic point here is, for the planets, they're very small compared to the moon. And so why pay for a big chip, or why use a camera that has a big chip if you're only using a little piece of it? And we'll talk about that shortly. And actually, as equipment goes, and for what these cameras do, this camera can save maybe up to 200 pictures a second. For a piece of equipment to do that, to pay $179 is a pretty good price. However, if, for example, you want to take a picture of the moon, which is much bigger than the planets, you do need a very large chip. And we see here, this is the actual chip that takes the images. It's about on the order of an inch in the diagonal. And these chips are, of course, much more expensive, but you need that if you're going to take a larger target, the moon or some other target. And then, depending on what you're doing, you may need a filter wheel, and that's about $600, and we'll talk about that shortly. But this is the basic equipment you need in addition to your telescope. So the first, we need a variety of pieces of software. The first piece of software is called Fire Capture. There are other softwares, I just happen to like Fire Capture. But one thing important is it's free. And there's a person in Europe, and he writes this program, and basically so the community can use it. And he's very helpful. He gives it away, and he accepts donations. But he's very helpful, and he answers questions, etc. And there's basically internet users groups where people post questions and answer each other's questions. So this Fire Capture controls the camera, and this is an example of, we see the moon here. So this is the equivalent of our computer chip with the moon on it, and we can control our exposure time. We can stop actual taking of the images. This is called a histogram, which we'll get into some detail shortly. This basically tells you how bright your image is. So this is a relatively simple program, and it's free, and this will run your camera. And what it does is it takes these pictures as fast as it can, and it saves them as a video file onto your hard disk. So the output, when you're done with this, is a video of however many images you want of these short exposures. So the next step, and this is not, you don't always have to do this, but if your image for whatever reason is jumping around, you can use this piece of software called Planetary Image Preprocessor, and again, this is free. So you load in your video, you tell it you want to align your images on Saturn, and what will output is a video of that same images of Saturn, but now Saturn's not jumping around. And it helps with the later software. So the next step is the selection and averaging. And I happen to use AutoStacker, and again, this is free. And there are people who they write the software for fun, and they make it available, and there are users groups. You can ask questions and get answers. And what this program does is it takes your video in, and you have to set it up, and the output is a single nice image. So what you do is you select Open, and you select your file, and then you click this button, Analyze. And it will go through all of your images. In this particular case, there are 4,976 individual images of Saturn. And it will go through all those images, and it will make a judgment on how good they are. And the output is this chart here, where the x-axis is your image number, and the y-axis is the quality. So with this gray line, image number 1 is on the left, and image number 4,976 on the right, and this gray line, which we see is going up and down and up and down, that's our quality. And this is representing how we saw Saturn constantly jumping around and changing. That's represented by this gray line. Now, and the green line is simply the same information, just plotted from best on the left to worst on the right. So after you do that, you then have to decide how many of these images do you want to keep. Now, in this particular case, I selected 1024. It does take a bit of practice to get to know how many to use. Or if you want to, you can set several different numbers, and it will several different amount of images, and it will basically do them all at one time. And you also have to tell which pieces of Saturn to do your alignment, because remember, Saturn is jumping around, and we have to align it very carefully. So in this particular case, there are 6 boxes, and it will align each image on these 6 boxes. And out comes your single exposure, which basically looks like this, just without those boxes around it. And the last piece of software, as far as working on the planets and such, is called Registax, and I use this for what's called wavelet processing. And it's just a fancy word for doing some image processing to draw out some of your fine details. So this is a typical image of Saturn. We see that Saturn has these nice bands. We see the nice rings. We see this break in the rings called the Cassini division. Actually, if you look close, you can see the disk of the planet through the Cassini division. It's actually a space in the rings where there's nothing. So you can see that faint little piece of the planet actually through that Cassini division. So this tells us that we end up with a pretty good image. And so again, your output is a single image that is an average of this n, which you picked later. In my particular case, it was 1024. So that's the basic lucky imaging process. So now we'll look at some results. So this is a series of Mars, which we did back in August of 2018 with the Schupmann telescope at Stellafane. You have to keep in mind that it perhaps is difficult for a person who hasn't looked at Mars through a telescope. Mars is very, very small, even when it's at its biggest in the sky. So you have to use a lot of magnification when you're looking at it through the telescope. But whenever you use a lot of magnification, it's just like going up close to a TV. The closer you get, the worse it looks. The same thing with looking through a telescope. So when you basically looking at Mars, it looks, because Mars is mostly red, you kind of have a red-orange blob, and it's really difficult to see the surface features. So the point is, try to keep that context. When we see these surface features on Mars, this is actually a pretty good image. Even though they might seem a little subtle, it would look much, much worse. You would never, ever see this with your eye. So all these surface features on Mars are real geological features that have been mapped out and named, etc. And this is the polar cap, the southern polar cap, which is ice of carbon dioxide, which melts and thaws and refreezes with the seasons on Mars. And these pictures were taken every few minutes, as we can see in the timestamp, and if you look close, you can see Mars is rotating. In this particular case, we used an infrared filter because at this particular time, Mars is basically one big desert. It's all basically sand and dirt, and there were big dust storms. So basically, if you looked in the visible with your eye, you'd just see a blank disk. But with the infrared, we could see through the dust. And again, the seeing must have been not that good because we had it set to 9 inches instead of 13. And this is a blow-up of an example we did of Mars at 9 inches and with 13 inches. So we see the 9-inch version is a little darker because we have less light, but perhaps that some of the fine detail might be a little bit better. So this is a picture of Jupiter using a red filter. Again, that same summer, summer of 2018, and it was good seeing, so we used the full 13 inches of aperture. This is the great red spot on Jupiter, and there are many, many fine details of all kind of festoons and little features in the clouds. So this is a pretty good image of Jupiter. And again, you would never ever see this with your eye. This is the advantage of taking thousands of images, keeping the relatively few good ones, and then averaging the good ones. This is an example of Mars, Jupiter, and Saturn on the same night, July 4th, 2018. We see here Mars is about half the size of Jupiter. This happened to be Mars was very close to Earth at that time. Mostly Mars is very small compared to Jupiter. And then we have Saturn here. And these are all pretty decent images. This is a time series of Jupiter. We'll look at some of these closer shortly. But this was using a color camera. We can tell that here. This is the camera we used. This MC means it was a color camera. And remember, we can, at this particular time, Jupiter was very low on the horizon because it's far to the south. And remember that the atmosphere, there's a lot of air when you're looking low. The atmosphere splits the color, but with the Schupmann, we're able to fix that. And if you look close, you can see that over time, Jupiter is rotating from left to right. And this is a blow-up of some of those pictures. And we see, again, a lot of nice detail. And it's nice to use the color camera when possible. And then this is the blow-up of the best image. This is this circle is called 1 arc second. 1 arc second is, there's 3,600 arc seconds in 1 degree. So there's about 2,000 of these that go across the moon. So you can see how much bigger the moon is compared to Jupiter. Jupiter is probably about 45 or 50 arc seconds, where the moon is 2,000. So the planet, and Jupiter is the biggest of the planets. So you can see how small the planets are. And this is some pictures of Saturn, nice color pictures. We have, again, these nice bands, the nice rings, the split in the ring, the planet through the Cassini division, and there's actually this greenish pentagon at the pole, which is actually a real feature. And this is just some blow-ups of Saturn. Again, this circle is 1 arc second. If you can see any features in general below 1 arc second, it means you're doing pretty good. And another Saturn. And this here we can see, because we're looking at somewhat of an angle, this black part here on the ring is actually the shadow of the planet on the ring. So the sun is coming from the upper right, and the planet causes this shadow on the ring. That's a real feature. And this is a set we did of Mars last summer. Actually, in this particular case, even though we had the Schupmann telescope, we were using a monochrome camera. That's what the MM stands for. So we were using a set of filters, red, green, and blue, to create the color. And the reason we were using monochrome is because we also wanted to use the infrared. So this top row is a summation of red, green, and blue images put together, and then this bottom is the infrared. And you can see there's a lot of nice detail there on Mars. And also you can see over the time that Mars is rotating from lower right to upper left. Okay, so now we'll get to the moon. And also we'll talk about high dynamic range imaging. This image here on the left is what I would call a correct exposure. Normally when you're setting your exposure time, and these are on the order of milliseconds or 10 or 20 milliseconds, a millisecond is 1/1000th of a second, you always have to set it for the brightest point of your target. So and keep in mind that to a computer, a picture is simply a grid of numbers. So ignore the 2 on the right for the moment. Imagine a checkerboard imposed over this image, and it's just simply a series of numbers where the black is low number, 0, 1, or 2. The medium gray is a medium number, say 100 or 101, and the brightest is 200 or 201. This, again, I said we would talk about this again. This histogram, the x-axis is the numbers on this grid. This is called an 8-bit image, so the possible choices are from 0 to 255, where 0 is black, 255 is white, and in between are the grays. So this x-axis over here on the left is 0, over here on the far right is 255, and so you always want to set your exposure. I'm sorry, the y-axis is the number of pixels that have that number. So, for example, there's this little spike in the low because there's a lot of black. That's why we see this spike. And there are no very, very white images. That's why we don't see any spikes here. Because when I set this exposure, you always set the exposure, your maximum brightness, to be about 2/3 or 3/4 of the way from left to right. that means you're getting a good exposure. The problem is, some of these darker areas, the exposure is not correct for, because I'm setting the correct exposure for the bright region, so the darker regions don't have the right exposure. So one solution is to take more than one images, and you set exposures for different regions. So this middle exposure is again, this first image was 1 millisecond. This middle image is 1.5 millisecond. We see that now everything's a little brighter, but these bright areas are a little too bright. And we now have on the right, a 2 millisecond exposure. The darker areas are really nice, but now the bright areas are exposed. So this is not good. So what the software that works on the high dynamic range is it takes all three exposures and combines them, use the good parts from each one to make a final image. So that way you can get a correct exposure for all of the parts of the target. And so this is the result. Unfortunately, it doesn't quite come as nice on that screen as it does here. If you want to see it later here, perhaps. So this is the result. So again, this is called a high dynamic range image, and this raw image is 7,500 pixels across. So if we wanted to print this at 200 dpi, which is pretty good, your eye won't see 200 dpi, this image would be 3 feet across, and you would not see any pixelation. So, and we see that the exposure for the dark area and the bright area is good. The dark areas are not too dark, and the bright areas are not too bright. And this was done with the Schupmann telescope at Stellafane. Now some results from Mount Wilson. This is a set of Mars done in 2018 with the Mount Wilson 6-inch refractor. And we always have to use color filters with that telescope, regardless of where, even if our target is very high and is not receiving any color from the atmosphere, we always have to use filters, which I'll get to shortly. But this is a series of Mars, and we see again Mars is basically orange or reddish. And over this time, we can see how Mars rotates, basically from left to right. This is a picture of Jupiter and Saturn with that 6-inch refractor. This is actually a very good image of Jupiter. Obviously it's in color, and this is a compilation of red, green, and blue images. In general, when we take pictures from Vermont with our 13-inch telescope or 9-inch, we're basically limited by the seeing, because there's a reason that there are no professional observatories anywhere within 2,000 miles of Vermont, because it has bad seeing. That's why by the size of the telescope. So in order to do better than this, meaning seeing finer details, you need a bigger telescope. This is an image of Saturn with that same telescope, and you notice that it has kind of a blue tinge, and that's because, as we spoke of earlier, when you have white light going through a lens, the lens splits the colors up. Now this lens we have in the 6-inch lens at Mount Wilson, it does have a However, the particular design they used, the blue, is very much out of focus from the green and the red. So in order to fix that problem, normally you use for the red and the green 100 nanometers. Basically, it's 1/3 of our vision. 1/3 is red, 1/3 is green, 1/3 is blue. But because the blue is so out of focus, we have to use a narrow band filter to focus the blue. And that means we're cutting down our light, which means we have to have a long exposure, which means that real-time blurring you saw of Saturn has more chance to ruin our images. So basically we're not as lucky. And that's why the blue is always a little bit worse than the green or the red with this particular telescope. This is a comparison of Jupiter with 3 telescopes at Mount Wilson. On the left side, it's the 6-inch refractor. In the middle is a 16-inch catadioptic telescope, a modern telescope you can go out and buy today. And then here on the right is with the big 60-inch at Mount Wilson. Now, strictly speaking, it's not necessarily fair to exactly compare these because they were all taken on different nights. So maybe the blurriness from the atmosphere might have been a little different. But in general, I think that the best one is the center one with the 16-inch because it's kind of a good combination of a bigger telescope than the 16, but it's not too big. Remember, we saw before that as your telescope gets bigger and bigger, the chances of getting good image become very much less and less. So that may be the reason why the medium-sized telescope produced the best image. And this is the Great Red Spot, and these are all compilations of red, green, and blue single images. These are some close-up pictures of the moon with the 6-inch telescope. This is the straight wall. And these are just a variety of random craters. These are the name of the major crater in the region. These are just some other high resolution images with the 6-inch telescope. And this is a comparison of the high dynamic imaging versus just using the single, quote, good exposure. Here on the left side is the single exposure, and here on the left side is the compilation of the 3 exposures. And when you get to a point of this, it's more art than science. So basically, you can choose which one you like. There's really no right or wrong answer. But this, if you're interested in a lot of fine high contrast details, this high dynamic range image has a lot of these details. And when you're making this image, you can adjust how these details look. It's basically just whatever you like to see. And just as an example of exactly how good the seeing is and the 6-inch telescope at Mount Wilson is, this is again a full high resolution full image of the full moon. And what I did was I just took this little piece and just cropped this out and blew it up. This is the crater Plato, and you see all this fine detail on the crater Plato. This can only be done with very, very high quality seeing. We can never do this, I think, in New Jersey or anywhere on the East Coast. All these fine, tiny little details. And this is an example with a 4-inch f9 refractor. And these are from New Jersey, so you don't need much of a telescope, and you can do some good work here. This is, again, on the left side, the standard image. On the right side, high dynamic range. There's no right or wrong answer. You pick the one you like. And here's another example. And this is an example of an image from an iPhone. This image, I didn't take the original video, but somebody took a video of the moon through their telescope. I downloaded it off the internet, and I did the processing. So, and this image on the right is one of the images from Mount Wilson. Of course, they don't compare, but it just shows that with an iPhone and a small telescope, using this technique, you can do some pretty nice work. And also, just as a final slide, this high dynamic imaging technique doesn't have to just be used in astronomical targets. This is a picture of the Stellafane pink clubhouse, which I took. The lower right is the single standard exposure. I ran it through the high dynamic range technique, and all the nice details and color come out. Again, it's more art than science. You can pick the one you like. So that's it. If anyone has any questions.
All right. Thank you, Tom, for the great presentation. Thank you, guys. So we are going to be doing a Q&A session now. I've put out the alert to our online viewers that, hey, we are having the Q&A session now. So what I'm going to do is I'm going to ask for a question from you guys, and when you raise your hand, wait for me to come over there with the microphone so that the online audience can also hear your question, because you might have a question that they want to hear the answer to. I also have a couple questions from our online audience, so yay. So to start, is anyone here have a question?
So everyone knows too, Tom, that maybe you were a little professionally modest when you said, oh, this is a pretty good result, and this is a pretty good picture. Those are really good results and really good pictures.
Yes, so because I'm not sure my online audience could hear it, Paul, our president here at UACNJ, had pointed out that Tom is far too modest, so, and that he should give himself a little bit more credit for some really nice images. All right, so any questions here, or shall I start off with one from online? All right, looks like I'll start off with one from our online audience. All right, the first one said, in the beginning of the presentation, I got this question. The graph with the lines look very much like mathematical functions you would learn in high school, where you have, and I kind of noticed that as well, where you have the logarithmic, and then you had the exponential.
Exponential, yes, that's this
and
equation
I
here.
forget whether it's sine or cosine. I forget which arm goes up or down for sine or cosine.
So what's the exact question?
Are they do they end up being that mathematical, or does it happen to just be a coincidence?
I'm just thinking a second how to answer.
Yeah, I think it was on a chart before this.
This scientist, Fried, basically studied the physics of the atmosphere, and he came up with this equation. What I suspect was that this is kind of a close approximation to reality, because the atmosphere is actually so complicated. So he kind of he had to simplify it a little bit. However, it's also true that many things in nature have these nice equations, like you were talking sine, cosine, exponent, and such. So the simple answer is yes, this is similar to stuff that you'd see in school. And I believe that many things in nature at least can be approximated that way.
All right. Was there a question from, or shall I do another one from online? Is everyone shy? Is everyone awake? I do hear the cricket back there, so I'm not sure. Oh, at least I got some giggles, so I know people are in fact awake. All right. So the next one is, what is the difference in the lucky imaging technique that you use and the ones that perhaps current astrophotographers might use? Or are you all kind of singing from
what's the definition of a current astrophotographer?
I honestly don't know. This is the question that popped up.
Okay, well, I guess there's, I'll answer it this way. There, perhaps astrophotography can, at least for the sake of this question, can be divided into two categories. One is, and it depends on the target you're interested in. One would be short exposures and one would be long exposures. So for example, if you're taking a picture of a galaxy or a nebula, you have to take a long exposure. And what happens is, if you look at the picture of Saturn, the live picture of Saturn here, if you took a long exposure of this, Saturn would basically blur out because it's moving around. It's the reason that in the pictures from the 6-inch at Mount Wilson, the blue is blurry because the blue had a longer exposure and gave Saturn time to move. So if you're taking a picture of the moon and the bright planets, you can take exposures that are short enough that it doesn't give them a chance to move. It's called, the lingo is called, the term we use to describe this phenomenon is called seeing, S-E-E-I-N-G. It's just a lingo term that means how good your view looks. Good seeing is nice and steady, and bad seeing is blurry. So what Lucky Imaging takes advantage of is short exposure, which, quote, freezes your seeing. It doesn't give Saturn time to move. But that only be done on bright targets. If you're taking a picture of a dim target, you have to take a long exposure, so you're forced to allow your target to get a little bit blurry. You have no choice.
All right.
So I believe that's,
so you're saying that both types of astrophotography use a similar technique. The difference is in how long you're exposing.
As a general point, yes.
Okay. All right. Question? Someone? Bueller. Oh, there we go.
Hi, so I was wondering, you mentioned that monochrome is better than color in some instances. Is that because of the infrared, or is that just for the contrast and being able to see details better?
Okay, perhaps I shouldn't have used the word better, because it is somewhat subjective, depending on what you want to do. If you want to take a monochrome red image, then that's fine. But there are certain instances where you have to take a monochrome image, like the old refractor at Mount Wilson, because it does not correct for the color, even from itself, forgetting from the air. All of the images the colors are blurry compared to each other. So in order to take a nice image with the 6-inch refractor at Mount Wilson, you must use a monochrome. If you used a color, you would get a subpar image. However, if you're using, say, a Schupmann or a Newtonian or something like that, and you want to take a color image, then if that's what you want, that's fine. Also keep in mind, it also depends what your goal is. If you're, quote, just want to take a pretty picture, you can do whatever you want. But let's just say you wanted to be an amateur scientist. In general, for science purposes, you have to take monochrome images. Partly depending on what you're doing, but probably most of the time that's the rule. So it really depends on what your goal is.
All right. I do have one last online question, and I think part of it has to do with the bit of phrasing. You had mentioned that the smaller telescopes are slightly better for imaging within reason, but then why do people get the bigger telescopes? Like, I know we have a 25-inch that eventually we will get the permits to get the observatory built, and we have a member club that has a 50-inch. So,
a telescope is a tool, and any tool should be optimized to do the job that you want to do. So just like you don't use a screwdriver to hammer a nail, it's kind of the same idea. So yes, it's true, you can use a 25 or a 50-inch telescope to image Saturn the same way I do here. And under the correct conditions, it will do a very good job. It's just that the chances that those conditions are good enough are much less the larger the telescope. So if you happen to be, say, at Mount Wilson in California, which has very good seeing, and it was a very particularly good night, then yes, a 50 or 60 or 100-inch telescope would do a good job, and it would do a better job than the 6-inch. But if it's a poor night, then the smaller telescope would do a better job. So, for example, in New Jersey has a general the seeing is much more poor than Mount Wilson in California. So on average, a smaller telescope for this particular purpose would do a better job. However, if you wanted to take longer exposures, as we were talking about before, of a galaxy or a nebula, then your resolution of your image is controlled by the atmosphere, and your goal there is to collect as much light as possible. So then you want to have a bigger telescope. So it really depends on what you're doing and under what conditions. But also it's again, to use a big telescope on a poor night, there's no point in filling up your hard drive with a bunch of blurs.
All right. Is there any more questions from our live audience here? Oh.
Hi, I have two questions. Thank you for your presentation tonight. I was wondering, you mentioned that the seeing on the East Coast is, always going to be worse than, say, the West Coast. Could you explain why?
Yes. Just like when you put a lens in front of your eye, whether it's a telescope or glasses, it alters the path of the light. Well, the atmosphere is like a zillion lenses, but they're also moving. So that's what makes Saturn jump around like this, is because you have these zillion lenses that are moving constantly. And these quote, lenses in the atmosphere are caused by differences of temperature. Each piece of air has a little different temperature than the piece next to it, and as the light goes through different pieces, it moves a little bit. Well, on the West Coast, the air is coming off the Pacific Ocean, which has thousands of miles of water, so it gets very calm. So basically all of these lenses are kind of lined up. So as the air hits the coast, it hasn't been disturbed. As opposed to here, we have 3,000 miles, the air has gone across the continent, and all the solar heating, just remember, like we talked about the mirage in the desert, the sun heats the ground heats the air. And so you have 3,000 miles to make all those disturbances. So that's why the seeing on the West Coast near the water in general is better than here.
Very interesting. Thank you. Okay, so my second question was, particularly in the image you showed with the moon, and then you showed us the up close picture of the crater.
Yes.
I was just wondering, can I assume that most of the time if you see a dark image that it means that there's a crater of some sort? That it's, that the Earth is going into itself, not the Earth, but the whatever you're looking at?
Well, the darkness, the moon is it's basically just dirt with no air. It's just basically rocks and dirt. So it's simply just the brightness of the particular rock. Now, in this image we see here on the left, most of those dark areas are like plains of lava, where lava came up like water and filled the region, and then it solidified a long time ago. And it just so happens that that particular rock is darker. So it's just a matter of just the color of the rock, literally.
Right.
But the answer is a dark doesn't only mean a hole, but it's essentially the color of the rock. But most of the dark does tend to be lower, but it's not necessarily a hole. It could be like an ocean, a huge plain, because these like this region here, that's hundreds of miles across, and it's solidified lava. But it's not. I wouldn't say that it's a hole.
All right. So I'm going to put a last minute call for questions for our online audience. If you have any more questions online, I do suggest getting those in quick. And was there any more questions from our live audience? Anyone? All right. So, just to give our online audience who do have a slight delay, because, things traveling over the internet aren't instantaneous, even though we'd like them to be. Just to reiterate a couple of things. If you do need the restroom here, the porta potty is right to my right, your left. We do have the gift shop. I do believe we actually do have an observatory open. I don't know if we're actually going to see anything, because we do have a lovely set of rolling cloud cover again. So, but on the bright note, we do we have, James, do you know if we have a presentation of past images up on one of the? Ah, yes. The perpetual problem of summer. It's lovely because it doesn't get dark till late, unless you're doing astronomy. Yes. That's always the problem. So, a couple things. You can check out our website, uacnj.org. We do have a list of all our current presentations, and we also have links on there to all our member clubs. We are an organization made up of other clubs. We do suggest that if you are interested in astronomy, do check out your local club. They, chances are, have a couple tips for your local area, like the best spot to see various planets or what you can't see in the area. And then they'll also be able to direct you to resources that you might not have known about. If you're up here, we do have the telescopes. Some are owned by United Astronomy Clubs in New Jersey. Others in those sheds are actually owned by our member clubs and operated. Oh, it sounds like someone's celebrating 4th of July a little early. All right, we also have our Facebook page, which you can always go and check out. We do have weekly articles posted there about various space topics. We also will post there if there are any special events, which we will also post on our website. We also are available on Twitter and Instagram. If you happen to take a good selfie of you guys on the overlooking rock over there or with a telescope, do tag us, hashtag UACNJ. So, well, all right. It looks like we don't have any more questions from our online audience, so I want to thank you all for coming. And just a side note, when you do decide to leave, do use your headlights. Yes, it ruins night vision just a little bit, but seeing the fact you're not going to run over a pedestrian is far more important, because it's really less than ideal to be that pedestrian that gets run over, which is why we wear safety vests here. All right. So with that, thank you, Tom, for a great presentation. And thank you guys for watching, coming out here. And thank everyone for watching online.